Alright guys, let's make a video here. Let's talk about some three-phase power and three-phase motors, okay? I'm gonna try to do this in one cut, so if my phone starts buzzing or whatever, we're gonna ignore it and we're gonna go on. And in case you guys haven't noticed, look at that jobs board over there. Holy moly. Wow, look at all those jobs. Zoom in on that. Pretty tempting for me. No, I'm just kidding. Alright. Let's talk about three-phase motor and three-phase power. So when we started looking at a three-phase building, there's three pretty common voltages that we deal with. The first one is going to be a 208 voltage building. So even this building right here that we're in right now, this is a 208 three-phase building. This particular, 208, this is going to come off of a Y transformer, and we'll talk about that in just a second. The next one, and guys, I'm no high voltage guy or anything, but the next one is 240 volt, 240 volt three phase. Not as common as 208. I'm not a high voltage guy, someone let me know, but I do know that it's easier for them to provide 240 volt to 240 volt three phase to a building than 208, but I don't know why, so I should probably know why, but I don't. This one's going to be off of our center tap. This one's going to be off of a delta transformer. You guys probably remember that, but we'll go back over that just a tad. And then the final one, we're going to talk about 480 volt. There's the phone. It also comes off of a Y transformer. So our 208 and our 480 or 460, whatever you want to call it, it's 460, 480, same thing. And 208, both of these are going to come off of a Y transformer, a typical Y transformer, where the 240 is going to come off of that center tap delta. This is the one where we're going to have the stinger leg, okay, the hot leg, the widowmaker, the whatever. Okay, this is it. And like I said, not near as common, but they're out there, and for sure out there. All right. And I got my cheat sheet here, right here. Let's talk about advantages of three-phase power. What are some of the advantages of three-phase power? Three-phase motors. So you take a three-phase motor and you compare it. Let's compare a three-phase motor to a capacitor start, capacitor run with a potential relay. So when you think about a capacitor start, capacitor run, a CSCR, we've got a run winding, we've got a start winding, we've got a potential relay, we've got a start capacitor, we've got a run capacitor, so the list goes on, right? And then you compare that to, say, just a typical three-phase motor that we're starting a cross line, XL across line, just going to send three-phase power to it. It's got three sets of windings, like there's nothing to it. She's a really basic girl. There's nothing there to fail compared to the capacitor start, capacitor run with the potential relay, with the start capacitor, with the run capacitor, so you guys know all that good stuff. So let's talk about, I'm going to go ahead and just put benefits right here. So the first benefit I just mentioned is that, man, there's not as much there to fail, right? I think everyone would agree with that. I've already said it twice, but what the capacitor start, capacitor run has, it's got run winding, start winding, potential relay, start capacitor, run capacitor, and on. Whereas the three-phase motor, if we're starting it across line, it's got a three-pole contactor, boom, and it's got three sets of windings, and that's it. So probably the first benefit is the simplicity of it, okay? It's simple. Three-phase power is simple. And we're going to get into part winding start and Y delta start and stuff. It gets a little more complicated, but compared to a single phase capacitor start, capacitor run with potential relay and all that good stuff, it's super simple. Okay? So with that simplicity, since we only have that three-pole contactor, and then we got three windings in the motor, which got three windings in the motor and a contactor, and that's it. It's super simple, and so we can also say that there's less failure points, right? So there's less failure points. We don't have as much stuff to fail. Just bottom line, less failure points. All right, so now let's talk about three-phase power, some more benefits. What's our starting torque like with a three-phase motor? And I hope everyone would agree that we have really high starting torque. We have really efficient motors with three-phase power. They're a lot more efficient. Higher starting torque, they run smoother, they last longer. And we can start just pointing all this stuff out, because when we start looking at what a three-phase motor does compared to a single-phase motor, when we start looking at the sine wave of 3 alternating current sine waves running this motor versus just a 240 volt single-phase capacitor run, we can also say it runs smoother. And you guys know all this, we've looked at it. And here's the other thing, because it runs smoother, we've got high starting torque, very high starting torque as a matter of fact. I mean, what else, there's nothing else that has higher starting torque than a three-phase motor. Nothing I can think of anyway, I don't know, but I would suggest that there's probably nothing then with higher starting torque. So we got high starting torque, we got that it runs smoother, and it runs, I'm going to go ahead and put runs smoother and more efficient. If you guys want to nerd out, if you're a heat and air nerd like me or whatever, right? Let me get down here in front of the camera. If you guys want to nerd out, you can go on YouTube and look up, there's this, I think the guy was an electrical engineer, if I remember right. But and I'll try to link it or something in this, on the canvas. But if you guys go on YouTube, this guy, electrical engineer, and he took three-phase power, and then he basically doubled it. And so now he's got six-phase power, and this guy was just nerding out on this stuff. He took six-phase power, and when he went from three-phase power to six-phase power, the efficiency doubled, the starting torque doubled, everything just basically systematically doubled, right? Proportionally. Everything went from 3 to 6, we went from three-phase to six-phase, everything doubled proportionally, right? And so he's like, well, hey, that's cool. And you guys look up this video, because he's just sitting in this chair and drinking coffee, talking about this stuff. And he even built the Highline wires, or he came up with a prototype, I should say. He built these Highline wires that could carry six-phase power. And so since his six-phase power went so well, he decided, like, well, hey, let's double it again. Let's go to 12-phase power. And so start thinking about that. And I'll go ahead and, spoiler alert, when he went from six-phase to 12-phase, everything didn't go, it wasn't the same exponential curve from 3 to 6 or whatever. Everything didn't double proportionally. When he went from 6 to 12, yes, there was some increases, but it wasn't an actual exact replica or actual double of what he already had, if that makes sense. I hope I'm saying that right. But when he went from 3 to 6, everything doubled. Starting torque, efficiency, like everything doubled. Like bam, 100% gain. But when he went from 6 to 12, there wasn't the same payback. He didn't get that one-for-one payback. It wasn't 100% payback. But check out the video. The guy's really cool. He's sitting in his little, lazy boy, drinking a cup of coffee, and he's talking about it. And they're putting these screenshots in, and it shows all the stuff. It shows the Highline wires that he came up with. Looks like a big dream catcher, kind of. He was ready to run six-phase power across the country if you listen to him talk. And maybe rightfully so, but who knows what that would cost to actually make that happen, right? I mean, that's crazy. But here's what's so beautiful about three-phase power. I better erase some more. Yep, not cutting that. So, here's the beautiful thing about three-phase power. So everyone knows we've got 3 alternating currents, right? We got L1, L2, L3. We've got 3 sine waves happening at the same time. So in black, look at this. There's L1. Look how beautiful that is. So black, I'm going to call that L1. We all know, you guys are all fourth and fifth semester, so we all know on single-phase power, E each wave, we're 360 degrees apart, right? I hope, surely, I mean, you guys know that, we're good with that. So each peak, we're 360 degrees apart. That's an entire revolution, or what, yeah. And so here comes three-phase power, here comes L2. So here's L2 in blue. Oh, I messed that one up, sorry. So L2 is blue. So we got L1, we got L2, and watch out because here comes L3. I got the red marker ready, right? So here comes L3. L3, I'm gonna have to fix some of this, but I'm wanting everyone to see, we're gonna look at the north pulses up here. And so here comes L3. Now let me clean this up a little bit, make it halfway realistic. Yeah, that's ugly, I'm sorry. There's some of it that's off. Use your imagination. One take. So now let's look at this. Let's just look at this for just a second. We're just gonna look from here to here. One 360 degree wave, right? 360 degrees. With three-phase power, you got to realize our motor is getting hit 3 times. It's getting pulsed, north, south, north, south, north, south, getting spun 3 times in every cycle. This is where the high starting torque comes from. This is where the high efficiency and everything comes from. These motors are smooth and they run efficient. Three-phase power is where it's at compared to single phase, right? And obviously less failure points and stuff like that, but this is where the starting torque comes from. So here, let me do this for you real quick. I'm gonna draw an imaginary motor real quick. So inside my motor, I've got a rotor that we're trying to spin, right? So here's my rotor inside my imaginary motor. And I'm going to put three-phase power to this motor. So watch out, here she goes. There goes L1. I'm going to keep this real simple. Here's my rotor. This is going to be just a pole, okay? I'm just going to put one right there. There's L1. That's L1. And I'm going to put just another simple in my make-believe motor. There's L2 right there. There's another pole. This one's pulsing north, this one's pulsing south. We're going to get that motor spinning, right? And then this one's pulsing, here we go, here's L3. So I got L1, L2, L3. So this rotor's sitting there, and as soon as I apply power to my make-believe motor, it's going to start pulsing north, south, north, south, north, south. I'm going to go L1, L2, L3. This is called phase sequence. L1 is going to stay on its black line. Remember L1 was the black line? That's phase sequence. L1 does not care what L2 is doing. And L2 doesn't care what L3 is doing. And L3 gives 0 darns about what L1's doing, and on and on and on, right? That's called phase sequence. Nobody cares what the other one's doing. They're going to just keep doing their own thing. L1's doing its own thing. L2's doing its own thing. L3's doing its own thing. So here's my rotor. I'm going to try to get this rotor spinning. So let's talk about phase sequence real quick. Well, if L1's pulsing north, and our rotor's magnetized, let's say this one's going north, this one's going south. Here's a $1 million question for you guys. How do you reverse the rotation on a 3-phase motor? Pretty hard, right? That goes along with phase sequence. L1 doesn't care what L2's doing, 2 doesn't care what 3's doing, 3 don't care what 1's doing, 2 don't care what whatever, okay? So, right now, in our make-believe motor, let's look at phase sequence real quick. It goes L1, let's just do it this way. It goes 1, 2, 3, right? Everyone agree with that? It's going to pulse 1, 2, 3. It's going to go north, south, north, south, north, south. And we're going to do a full revolution. Each one of these phases are 120 degrees apart in their timing. So between L1 to 2, 120 degrees. Between 2 and 3, 120 degrees. 2 2 and 3, I'm sorry, 3 and 1, guess what? Oh my goodness, 120 degrees. So that is a full 360-degree revolution, right? So our timing on our three-phase motors are 120 degrees apart in their timing. So, as this pulses, you guys know to switch the rotation on a three-phase motor, all you got to do is change any two leads. But do you know why that works? Let's talk about that real quick. Mathematically, it will always work in phase sequence. I think I've said that a time or two. So it's always going to go 1, 2, 3. So let's just pretend right now this thing's going 1, 2, 3, 1, 2, 3, 1, 2, 3. So it's going this way. It's going clockwise, right? So right now, this motor is spinning clockwise. Mathematically, if I change any two leads, I don't have anybody in here right now because it's 4:30, but so I usually say, hey, pick two of them. So let's pick two. It's a swap. Let's swap 3 and 2, okay? So now let's swap 3 and 2. So now 3 becomes 2, and 2 becomes 3. Guess what, boys and girls? Now it's going 1, 2, 3. 1, 2, 3. 1, 2, 3. Now it's going counterclockwise, right? And you mathematically, like, you can do this all day long. If you switch any two leads on this motor, it will change its rotation, okay? It'll go from clockwise to counterclockwise and on, back and forth. We're going to talk about voltage imbalance and current imbalance and stuff like that, and we'll talk a little bit more about that. Let me look at my notes real quick, see what else is next. Turn the page. Okay. This is just something goofy I like to do. I probably shouldn't do it on a video, but whatever. Here's a math problem for you. 3 minus 1. Okay? When we're talking three-phase power, like the answer is not 2. If I hear someone say two-phase, I cringe, and my 140-pound self is going to jump all over you. So don't do that. If you have, this is just a joke. If you have 3 legs of power and you lose one of them, you're back down to single phase. So I make this joke. 3 minus 1 equals 1, right? Is this thing recording correctly? Yes. 3 minus 1 is 1, because if I have three-phase power, if I lose one leg of power, I'm back down to single phase of power. So let me show you what I'm talking about real quick. Here's L1 coming down, feeding something, we'll get there. Here's L2 coming down, feeding power, we're feeding something, we'll get there. And then lastly will be L3, feeding some power. Here, let's say it's feeding a contactor. I'm going to just draw some contacts up here. Look at how good I can draw. All right. When I go from L1 to L2, I have a potential difference. I'm going to read the full potential, right? So if it's in our building here, between 1 and 2, L1, L2, line 1, line 2, I should read 208, right? And from 2 to 3, I should read 208. And from 1 to 3, I should read 208. No matter which leg, no matter where I go, there should be a potential difference of our full applied voltage, right? Okay, so I'm going to do something else right here. I'm going to put a ground screw. Let's say we're in a disconnect or we're in a package unit, a rooftop unit, whatever. And so I'm going to add a ground screw right here, or a ground whatever. There's a ground. I'll get there. So let's say that we lose power. Let's say that L2 blew a fuse. So L2, I'm going to just write blown fuse, even though you probably can't, whatever. Okay, so L2 is dead. L2 is dead. Now, when I go from 1 to 2, there's no potential difference there. I'm probably going to read 0 volts, right? Probably. If there's nothing else tied in here, we'll talk about that. But between 1 and 2, I'd read 0, potential difference, based off of this drawing. And between 2 and 3, I'd read 0 potential difference. And between 3 and 1, I'd get my full potential, right? So in this building, it'd be 208. Okay. Here's what'll burn a lot of guys. They'll see that 0, 0, or they'll see something goofy, like 120. Here's what will throw you off, okay? On every rooftop unit in the world, every package unit, whatever, every unit in the world, if you look at the line side of the contactor, okay, so we're going to pretend that this is the compressor contactor, these 3 contacts I got up here, 3-pole contactor. If you were to look up here on the line side of the contactor, there's always stuff tied in, right? Stuff that we need powered 24/7, 365. Simple things like, maybe there's a crankcase heater right here between L1 and L2, crankcase heater. Or, most common, what if the primary of our transformer? So what if the primary of the transformer is between 2 and 3? So there's the primary, here's my secondary, here's my 24, whatever. But the big thing is that my primary is tied between 2 and 3 on this 208 unit, right? Okay. What'll happen, and I get this call quite a bit, people are like, oh, I got weird voltage, I got 208, and I got 120, but then here's the kicker. They'll say, when I check each leg to ground, they're taking each leg and comparing it to ground, they're like, man, I got 120 on L1. I got 120 on L2. I got 120 on L3. When I check each leg to ground, I've got 120 volts. 120, 120, 120. But when I go leg to leg, I've only got 0 or 60 or 120 or some goofy, ghost number. Guys, the reason why is because you have your crankcase heater and you got your primary of your transformer and all this other stuff tied in on the line side of the contactor. This will burn you if you let it. Don't let this burn you. This is something silly, so burn this in your head. Don't let it burn you. So, let's talk about checking each line to ground. L1's hot. The only thing we've lost is L2. So L1 is hot. If I check it and compare it to ground, if I've got a good ground, on a 208 building, I'm going to get 120 volts, right? L3 is hot. I'll skip L2 on purpose. L3 is hot. So if I check it and compare it to ground, I'll get 120 volts on a 208 building. But then we know L2 is dead. Remember, I even wrote it up here. It's got a big blown fuse, right? There's no power at L2. But when you check at the contactor down here, and you come in, you're working on this rooftop unit, and you're just checking on the line side, or you're in the disconnect, and you're checking in the disconnect for a blown fuse or whatever, you're going to go from L2 to ground, and you're still going to get that 120 volts. And you're going to be like, what the deuce, right? I've got 120, 120, 120, but when I go from here to here, 2 to 3, I got 0 volts. And guys, the reason why, we know, I already told you we got this blown fuse, but when you check L2 to ground, and you see that 120, we're back feeding. Because look, we got L3 coming in, feeding the primary of the transformer, and it comes in, it's sitting at L2. It's trying to get back on L2, but it can't because it's got a blown fuse. And so what it does, whenever we put our meter right here, and we check from L2 to ground, you see that 120? We're actually reading this L3 that's coming down, going through the primary of the transformer, and then it's sitting here at L2 trying to find its potential difference, trying to get back to the other side of the line, right? And it can't because we got a blown fuse. So whenever we check right here and compare it to ground, we're going to see that 120 volts because L3 is coming over and it's back feeding through the primary, and it's sitting right there, right, trying to get back to the other side of the line. This may not be the best example because this one would actually get back to L1. I may not have drawn it perfect, but use your imagination, all right? Same thing here. L1 would come down and feed through the crankcase here. I got an idea. There is no crankcase heater. She likes it. She don't care. So now we just got the primary, the transformer, and that's why you would read 120 volts from that dead leg to ground with your voltmeter, okay? All right, there's your funny math problem. 3 minus 1 is 1. If you have 3 legs of power and you lose one, you're back down to single phase, okay? Real quickly, I think everyone should be really good with this, but this will come in handy later when we start talking about Y delta start. This is a Y configured motor. Okay, it looks like a Y, right? Like, wow, I bet you that's why they call it a Y. Amazing. And then we got this one. And this one's delta. It's not because it looks like a delta. Well, I guess it is. It looks like the Greek symbol delta or something like that. So, Y versus delta. And we're going to get into this when we start talking Y delta start. Delta is a lot more powerful than Y. And Y only has, from most of the stuff I've read, like if you take the same exact motors with the same exact resistance, same exact voltage, everything like that, most of the stuff you read will say that a Y only has about 1/3 of the starting torque as a delta. But what happens is, what if you're trying to start a centrifugal chiller, or what if you're trying to start a turbo core or something like that that's spinning 30,000 RPMs? You're not going to be able to take that motor and just close a contactor and start it across line. We're going to have to soft start it. So in today's world, we'd probably put it on a drive, on a VFD, and we would do a ramp. And you know, the name of the game is bring it on, leave it on, match the capacity, all that good stuff. We don't want to cycle anything off and on. We want to bring it on and leave it on. Startups kill compressors. But anyway, we're going to get into this where we're going to start talking about centrifugals that aren't on a drive. Some of the older stuff, it's going to start as a Y, run as a delta, and then we'll use inlet guide vanes to vary the capacity. Basically, inlet guide vanes on a centrifugal are just going to block the suction gas coming in, and that's how you vary the capacity on a centrifugal. But we're going to soft start it. The big thing is we're going to soft start it as a Y, and then transition to a delta after it gets up to speed, just to limit the inrush current. That's the name of the game on soft start stuff, is to limit the inrush current. We want to limit that peak, right? All right. Let's see what else I got next. We talked about the advantages. Hey, here's one advantage I didn't mention. It's just a small advantage, but 3-phase power is actually just a small bit cheaper to buy from the electric company compared to single-phase power. I guess I got to do less work to it. Again, I'm not a big, I don't know anything about the high-line wires or anything like that. But here's a fun fact. Can anybody think of any disadvantages of 3-phase power? I'll wait for that one. The only thing I can think of is like, the only disadvantage of 3-phase, the only disadvantage of 3-phase that I can think of, and if you guys think of something, let me know, please. But the disadvantage of 3-phase may be like the cost of the panels and stuff like that. You know, you go buy a single-phase panel, breaker box panel, versus a 3-phase panel, or in our world, like we go buy a single-phase disconnect, right? So I can get a 60 amp single-phase disconnect for like $9 from my boys at AMSCO, fusible disconnect. But you go look at like a 3-phase disconnect, and you know they're $100. And if you need a 600 volt, it's a gazillion dollars or whatever. That's the only disadvantage I can think of, is you're going to pay more money for the panels, or someone's going to pay more money for the panels and all that good stuff. Okay. All right. And guys, remember, like, it's just like everything else in the heat and air world, that, and I'm kind of known for saying, like, as a human, we have this like human instinct or something to always point our finger at what we know the least about. You're like, man, it's got to be that processor or whatever, because I checked this and this or whatever, you know. And so as human nature, we automatically try to point our finger at the thing that we know the least about. So don't catch yourself. Don't let you get yourself like getting hung up on something and getting flustered and be like, oh, it's got to be that, because I've checked a few other things that I know how to check, but that processor or whatever. Man, there's a checkout procedure for everything. Find the test points and do your thing. Hit some service literature, all that good stuff. Okay. All right. On a 208 building, it will be a Y transformer. So that on a 208 building, your transformer is going to look something like this. It's going to be this is a 208 Y transformer. And right now, it just looks like a typical Y configured motor, right? But the thing is, on the transformer, our neutral tap is going to be right there. Our neutral tap is right there. So let's just assign these some names. L1, L2, L3. So now, if I go from leg to leg on this 208 building, if I go from L1 to L3, what voltage should I see? I should see 208, right? And here's the thing, when I go from any leg to any leg, I'm going to get 208. If I go from 1 to 2, 1 to 3, 2 to 3, 3, whatever, I'm going to get 208 on this 208 building. If I go from any leg to neutral ground, 3 to ground or neutral, 1 to neutral, 2 to neutral. If I go any leg to neutral, I will get 120 volts. And here's what trips people up. They'll say, hey, how come if I go from 1 to neutral, I get 120 from here to here, and from 3 to neutral, I get 120 volts? So how come when I go from 1 to 3, why don't I get the sum of both of them? I should get 120 plus 120. I should get 240 volts. And that's actually not true. And the reason why is because this transformer is out of phase, okay? There's loss. It's extreme. It's out of phase. Compared to, well, here, let's go ahead and let's just do this other one. Let's do the other Y real quick. Let's talk about the 480 volt Y. Guess what? It looks just like that one, okay? Cool. L1, L2, L3. This is a 480Y. So guess what? If I go from leg to leg, I'll get 480. If I go from any leg to any leg, I'll get 480 volts. 460, 480, plus or minus 10%. 480 plus or minus 10%. If we step over here to the Reynolds building right now, I guarantee it's running at 500 volts. It always runs, you know, so anyways, 480 plus or minus 10%. Leg to leg, if I go any leg to any leg, I'll get 480. Here's the kicker. If I go from leg to neutral ground, I do not get 120. As a matter of fact, if I go from any leg to ground, any leg to ground, any leg to neutral, I'm going to get 277 volts. If it's a 480 volt building, there is no 120 volts feeding that building off the transformer. There's no 120 volts most of the time, okay? So on this 480 volt building, I get 480 leg to leg. I get 277 from any leg to ground. So what can you do with 277 volts? The only thing that you can do with 277 volts is run the lights. See the light reflection on the whiteboard? I tried to fix that 100 times. It's impossible. So hopefully everything's cool. 277 volts, you can run some lights. We have ballasts that are 277 volts. And then all the multi-tap ballasts, all that good stuff that'll take any voltage out there. That's about all you can do with 277. Do not try to run a 240 volt motor on 277. Like, that's stupid. Don't do that. So how do you get 120 volts in this building, right? You can't, there's no 120 volts feeding this building most of the time. You can't get a 277 volt computer that I know of, or a 277 volt pencil sharpener. So the only way that we get 120 volts in these buildings is we have to set additional transformers. Usually they're in the mechanical rooms, right? I can run you guys over to the Reynolds building and look over there, it's 480, or the Noble Center, or whatever. And as we go into each mechanical room, you'll see a standalone transformer, several kVA transformer. All that does is take this voltage and knock it down to 120. So, with that being said, so anytime we have a 480 volt building, most of the time we have to set additional transformers just to get 120 volts to power our plugs and stuff, right? So here's my question to you guys. What is the advantage of 480 Y versus 208 Y? I'm going to pause for a minute. What are the advantages? And guys, I'm going to tell you, even though mathematically it's not, electrically it is double, okay? 480 is exactly double of 208. And what I mean by that is when we start figuring in Ohm's law and stuff, if I have a, like an RTAA or what, if I have a chiller, some kind of screw machine or whatever, 100-ton screw machine, and it runs on 208. Well, its full load amps is probably going to be like 400 FLA or whatever. I'm just making something up. So if at 208 it has an FLA full load amp of 400, what's it going to be when we double it? And if you said it's going to cut it exactly in half, you would be correct. So the amperage cuts in half as the voltage doubles, right? And that's a good thing because now we can run smaller wire to feed this stuff. If you're pulling wire out to a screw machine sitting outside or something like that, the electricians are, they're pulling their wire to their screw machine sitting outside. I don't want to pull this wire. I hope you guys can see. I don't want to pull that wire. I'd rather pull this cheaper wire, right? So the cost of the wire savings has to compensate and override the cost of those additional transformers and such that you're going to have to buy just to knock this down to 120 volts, right? And I'll go ahead and throw this out there. I'm sure you guys, all of our ACR students already know this. This doesn't help with the electric bill, right? Wattage is still the same. You're still paying the same wattage. Just because amperage got cut in half, the voltage doubled. So this is the same wattage as what we got going on here. So the electric bill doesn't change, right? I told you guys the story of my drunk uncle that wanted to replace his pool pump. He's like, that's a 120 volt pool pump and it pulls 15 amps. And I'm going to rip that thing out and I'm going to put in this 240 volt. I'm going to take out this 120 volt. I'm putting in this 240 volt pool pump. It doesn't pull 15 amps. It only pulls 7.5. Like, dude, like, come on. Like, it's the same wattage, right? We all know that we pay for wattage on our electric bill, right? Drunk uncle, take a walk, silly goose. There's no one here to laugh, so it feels kind of weird. You guys wouldn't laugh anyway. All right. The last one we've got. Let's talk about the 240 volt building. This is the only one that's offered the Delta. And like I said, I need to look this up, honestly. I know that it's easier for high voltage guys to drop a 240 Delta than it is a 208Y. Something about piggyback transformers. I don't know. Some kind of nonsense going on there. But anyway, I should know that. The the 240 Delta, obviously it looks like a Delta motor until we add our neutral tap into it. And our neutral tap is right here in the center, because this 240 Delta is also known as the center tap. It's tapped right in the center, right here, right? And so on this one, I'm going to give it some designations. That's L1, this is L2, and we'll say this is L3. I'm just making those up, right? So between 2 and 3, between any leg to any leg, any leg to any leg, 1 to 2, 2 to 3, whatever, we're going to get 240 volts. But the kicker on this one is from L2 to neutral ground, we'll get 120 volts. Bam. From 3 to neutral ground, we're going to get 120 volts. But this is the one, the center tap, the 240 Delta is the one that's got the stinger leg. So this L1, look at all the induction it's getting. It's like bam, 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 bam. And plus give me that bam, 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 bam. And so when I go in this scenario, I just made these up, L1, L2, L3. But in this scenario, L1 is going to be a lot higher voltage than 2 and 3. When I compare each of those to ground, L1 is going to be the higher voltage. And guys, that's called, you've probably heard this before from Mr. King and stuff, back in electrical, but that's called, as people call it, it's the center tap transformer. But that hot leg, it's called the hot leg, it's called the Widowmaker. What's it called, man? It's whatever. Stinger leg, yeah, all that crap, okay? But on that I'm gonna just call it the hot leg. On that hot leg, you're gonna get something higher than 120 because look at how much is being induced onto it, right? It's getting all this and all this, so on that hot leg, you're gonna get at least 180 volts. I'll just put like something like 180 to 200 volts, okay? So, what are you going to do with 180 volts? I won't give you very long to think about that because you can't do anything with 180 volts. It's worthless, okay? And I usually make a joke here, but it's worthless. It is completely worthless, completely worthless, completely worthless. You can't do anything with it. And so, because of that, this one becomes extremely hard to keep balanced. Now, if we look at a Y transformer, right? So if we look at a 208 building or a 480 volt building, we look at this Y transformer, and it's got the neutral right here. Every leg to ground, every leg to neutral, I get 120 volts. So this is easy. All my single phase stuff, if I need 120 volts for a bunch of lights in this building, I'm going to put a third of them right here. I'm going to put a third of them right here. I'm going to put a third of them right here. Between 1 in neutral, 2 in neutral, and 3 in neutral. I'm going to just spread them out in thirds. You need to keep this transformer balanced, okay? Because what will happen, what we're going to lead into, if let's say they got a bunch of single phase package units on the roof, and they put them all between, let's say this is L2 and this is L3, and they've got a gazillion rooftop units between 3 and 2. Well, guess what? 2 and 3 are sitting here doing all this work, running all these rooftop units, all these single phase units or whatever. L1 just sitting back here like, this is a joke, I ain't doing nothing. And so then you start getting into phase imbalance, okay? These are motor killers when we start getting into phase imbalance. We're going to talk about voltage imbalance and current imbalance, all that good stuff. But this is motor killers right here. You would not walk up to a $6,000 motor and condemn it and just slam another $6,000 motor in it, right? And just wire it up and flip the power, slap it on the butt, and wish it the best of luck. We're not going to do that. We're going to make sure, we're going to crawl this thing and make sure there wasn't something prior going on that caused this motor to fail, right? It could be a dirty power issue, it could be a phase imbalance issue, and all this other good stuff. I think I'm getting pretty long in this video. I'm probably better. Yep, I'm going to cut this video right here. Let me make sure, hang on one second. I told you guys I'm doing this in one cut. Let me make sure there's nothing else I want to throw in on this video real quick. it's important to keep your transformers balanced. I'm gonna throw one more thing in here. This is just a Boatner deal. Anytime, if you guys are doing startups, if you're gonna be on rooftops doing startups, for love of everything, if it's a 208 building, like, go into your 24 volt transformer, okay, and change it from the 240 tap to the 208 tap. So if we look at our 24 volt transformer, it's something like this. Artist rendering here, hang on. This is my 24 secondary. But what I got going on up here is I have a common tap right here. So on this common tap, I'm going to take L1, I'm going to feed this primary. So, I erased it, my bad. So L1 comes in and feeds this primary. It goes in and feeds the primary. And then I've got two possible options for L2. This is going to be my 208 tap. This is going to be my 240 tap. Guys, every rooftop unit from the factory is going to be wired into 240. And I already told you guys the 240 Delta is way less common than the 208. Unless you're working on a bunch of small buildings. But when we get into bigger buildings that have multiple units and stuff, like, it's going to be, most of the time, it's going to be a 208 building. Not always, but majority of the time, I'd say. So, but from the factory, they're wired in for 240. So what happens, you guys obviously know this, but what happens if I have a 240 primary, but I only apply 208 to it? What's going to happen to my secondary voltage? It's rated for 240 primary, that's the way it's wired from the factory. I only apply 208 to it. So my 24 is not going to be 24. We can do the math, it would be something around 19, 20 volts, right? And so you potentially could start getting some chattering and some other stuff going on. So, but the reason they do that, guys, is so that if they wired them all for 208 out of the factory, and then you put 240 to it, like, you're gonna end up with, like, 29, 30 volts, and then you may end up frying something eventually, right? So if you're the startup guy, if you're doing startups, I mean, this is kind of my go-to thing. Here, I'll let you guys in on my secret on startups. The couple main things I see, this is one that drives me crazy. I've seen 10-year-old units that are still whatever, but if it's a 208 building, take this off and move it over here to the 208 tab so that you actually get a true 24 volts coming out. The other thing, I'm just going through like inspections and stuff in my head, but all of our newer rooftop equipment, everything's more efficient now, right? The SEER rating's gone up, everything's gone up, our efficiency's gone way up. And so if you're pulling off a 20-ton rooftop unit and, it's got, its maximum fuse size is 100, and you put another rooftop unit the same size right in its place, and you look at its maximum fuse size, they're always smaller. So make sure you fuse down the disconnect. When I do a startup, I guess that's the first two things I check. What's the maximum fuse size? What's in the disconnect? Make sure the fuses match, because if they didn't change them, there's still the big fuses for the old inefficient unit. And then this is the next thing I check. Make sure those are just my first go-to things, because I've been hurt too bad on inspections on the fuses. And then this just is kind of a pet peeve of mine, I guess. But guys, I gotta shut it down right here. I've talked a lot longer than I thought. Y'all holler if you need anything, and I'll get some more of these going here for you. See ya.